We're now going to examine the wave equations using harmonic waves. So harmonic waves are the simplest form of wave we can consider. In essence, a harmonic wave is the form of a sinusoidal disturbance of a string excited by an object undergoing simple harmonic motion. So we have an object somewhere on the string undergoing simple harmonic motion at an origin, which induces this harmonic wave through the string. The shape of the wave is a sine cosine wave, and it has defined features such as its wavelength, its amplitude, and so on. We call this a harmonic wave because it is stimulated by simple harmonic motion, and we can consider every point on the string to be undergoing transverse simple harmonic motion in the case of this transverse wave we are showing. The defined features that we can determine are the wavelength, which is the spatial repeat distance of this wave, the period t, so the time it takes for that wave to complete one cycle, and the frequency of the wave, which is simply 1 over the period. In a harmonic wave, we have a single amplitude to consider and a single wavelength, so it is a simple wave to look at. We're going to consider transverse sine and cosine waves because, as I say, these are the simplest to consider. During a period t, the wave moves through its distance lambda, so we can calculate the phase velocity of the wave by the ratio of the wavelength to time, which is f lambda, which is an equation which you are most likely familiar with, so relating the phase velocity and the frequency in hertz. At any instant in time, we can define the y disturbance, so the localized disturbance of the medium, as a function of the position and the phase shift delta. So we have the amplitude, the phase constant, and we can set the origin so that delta equals 0. In this case, k is a constant scaling wave in the x direction. Now this equation will look very familiar to you from the simple harmonic motion oscillations part of the course, but it's really important to remember that once we start talking about waves, this k value is not a spring constant. It is just a scaling constant in the x direction. So we'll talk more about that later on. We said that the wave is periodic. So what that means is if we have a sine function of kx, we can say that the sine function of kx plus lambda, x plus a single wavelength, gives us the same value. This allows us to find a value for k. So if sine kx plus k lambda is equal to sine kx, that must mean that k lambda is equal to 2 pi, or k is 2 pi on lambda. In this case, k represents the wave number of the wave, and the units of that is radians per meter. If we have a high value of k, that means we will have a short wavelength, and consequently we will have a high energy in the system. We'll look at an example considering frequency and velocity. So what happens to the phase velocity v and the wavelength lambda if the frequency of the wave is doubled? Pause the video and we'll discuss it afterwards. So the key equation we're looking at here is this v equals f lambda. So this is the key part that we're looking at. Simple analysis of this equation, however, doesn't tell us exactly what we need to know. The thing we do know is that we're on the same string, and we said earlier that the phase velocity is a function of the material through which the wave propagates. So what that means is if we're not changing the wave, we're not going to change the velocity. Okay, so that means we either have b, d, or e. Let's now look at what happens to lambda. Well, if v doesn't change and the frequency doubles, that must mean that the wavelength is halved. So our answer here is d. The speed doesn't change because it's a property of the string. Doubling the frequency will have to halve the lambda because v is a constant in a given material. We now want to think about travelling waves. So what happens as waves travel through a material? So at any instant in time, we have the wave equation. For a wave travelling to the right, we can replace x with x minus vt. So we rewrite this as a sine kx minus vt, or a sine kx minus kvt, and that wave is repeated for every period t. So what that means now is that we can now replace t with t plus capital T, which gives us the overall wave equation here. In this instance, we already know that kvt from the start here must equal 2 pi, which gives us the relationship between the wave number, the phase velocity, and the period t. From our discussion of oscillations, we know that the period t relates to the angular frequency omega. Putting these two equations together allows us to find an expression for the phase velocity. So we can say that the phase velocity is equal to omega on k. So for a wave travelling to the right, we can now substitute v for omega on k, and we end up with an alternate representation where y equals a sine kx minus omega t. So omega, the angular frequency of the wave, k, the wave number of the wave. Let's look at this in context. Let's consider the behaviour of a transverse wave. So we have a description of a wave on a string described as a sine kx plus omega t. In what direction is the string and the wave moving? Pause the video and we'll discuss it presently. The simplest thing to consider at first is the movement of the string. So a particle of the string, or a component of the string, because it's a transverse wave, it will move in the plus or minus y direction, so perpendicular to the direction of propagation. Now the wave will move, as we say, in the perpendicular direction to y, so we need to think of whether it's moving in the positive or the negative direction. Remember, there's an inverse relationship between the two, so if we have plus omega, we have a negative direction that it's moving in. What that means is the wave will be moving to the left, so it'll be moving along the x-axis to the left. Just as with oscillations, we can have a complex representation of a wave. As we said before, the sine and cosine functions all satisfy the wave equation, which must mean that complex functions must satisfy it too. Do go back to the simple harmonic motion section if there's any confusion over this. Sine waves are given by the imaginary component of y, while cosine waves are given by the real component of y. And we'll use this as our ongoing treatment of waves. In summary, when we look at harmonic travelling waves, the wave is described by a sine kx minus plus omega t. We've represented it like this because of that reverse relationship between omega and the direction of x in which it moves. Remember, negative omega, positive x movement. Negative omega t means travelling to the right, while plus omega t means travelling to the left. We defined a wave number, k equals 2 pi on lambda, which allows us to define the phase velocity v as equal to the angular velocity divided by that wave number. And all of these equations we'll be using to build our understanding of waves travelling through media.